Yeah, thank you. Thank you so much for joining this lesson. Good morning, good afternoon, good evening. Wherever you are most welcome to today's lesson. We shall be discussing Mokasa 1 joint examination. So we shall discuss actually the full paper. So you better tighten your belts now because we are going for the 80 marks. As we continue learning, please remember to subscribe to this platform and also share to invite your friends. Remember also that we have our one-on-one classes, which are going to be happening via Google Meet from 13th to the 24th of April 2026. Use the number on the poster 07 04 15 3366. You can reach out for more details about the programs. Remember also that we have a schedule for the junior school. So if your brother, your sister, your friends are in junior school, you can also invite them through the same number. Back to the paper now. Number 1, list any one advantage of using optical fiber in telecommunication over ordinary cable. This is from 3 physics, total internal reflection, because the optical fiber uses total internal reflection concepts. So you're supposed to know that the topic, before you respond to any question in physics, please, first of all, place the question in its context so that you may respond to the question in the proper way. When you answer a question without understanding where the question has been extracted from, you are likely to mess up. So my advice is, let people know where the question is coming from. This is from 3 work. We call it refraction of light. That is topic 2. Total internal reflection is the concept. Now, applications of total internal reflection, where optical fiber is one of the applications in telecommunication. So it has higher carrying capacity when we compare it to the ordinary cables. Higher carrying capacity. Higher carrying capacity. It has a higher carrying capacity. There are many other advantages, but the examiner demands only one. They are also thinner and lighter. They are thinner and lighter. So they are easily portable, in other words. There is number 2. This is from the same topic. From the same topic, geometrical optics. That is the branch of physics where it lies, refraction of light. Now, the diagram of a slab of uniform thickness lying horizontally, a ray of light is incident upwards on the surface of the glass and is refracted successively at A and B, the points where it crosses the interface. So this is point A, this is point B. Look at the first question. Determine the refractive index of, for the glass, given that its critical angle, C, is equal to 42. We all know that refractive index can be given using very many parameters. We can use what we call angle of incidence and angle of refraction. We can use critical angle. We can use speed of light in the different media. So those are all options. We can also use actually real depth and apparent depth. So refractive index is a constant that can be obtained using several approaches. Now with critical angle, we know that refractive index, small letter n, is equal to the sine of C, where C is the critical angle. So 1 out of sine 42. You type this one into your calculator. The critical angle is the refractive index is confirmed to be 1.494. No units for refractive index since it's a ratio. We also taught to find the angle marked X. Here, you know the medium here is glass. And we know that now we have two medium here. There is air and there is glass. Now, when we're having an angle of 60 and you're having an angle of, okay, angle X there, and we have refractive index for the two media, then we usually say this, refractive index of air, refractive index of air multiplied by the angle at air equals to refractive index of glass and also the angle on the other side where there is glass. So as the ray of light enters the glass, it makes an angle, and as it penetrates the glass, it makes an angle of X. So there is X and 60. The refractive index of air is 1 multiplied by the sine. Actually, there is sine, sorry, it's sine of the angle. Sine of the angle. You know, it's good for you to know that initially we talk about refractive index of the first media times the sine of the first angle should be equal refractive index of the second sine of the second angle. That's why now, to be more specific, we are talking about refractive index in the air, sine of the angle at air equals to refractive index once the light penetrated the glass, then sine of the angle it makes as it penetrates the glass. So 1, that is refractive index of air, times the sine of 60 equals to 1.494, the sine of the unknown X. At this point now, we can remain with X. Okay, let's talk about the sine X first. We can solve it stepwise. Sine X equals to 1 times the sine of 60 divided by 1.494. We're getting a 0.5797. So that to remain with X, we talk about the sine inverse of 0.5797. So shift sine, this is going to be 35.43. 35.43. That is now the angle to 2 decimal places. If you're getting something, please type I am learning. I am learning. Yeah. If you get something, type I am learning. Let us also know where you're watching us from. Let us know where you're watching us from. I am learning from Nairobi, from Kisumu, from Makueni, from Machakos. I am learning from Kitui, from Kiambu. Just tag your county, tag your school. Let us know where you are getting us live from. Number 3. Now, a fishing boat uses ultrasound of frequency 60,000 hertz. You remember 60,000 can also be written as 60K hertz to detect fish directly below. Now, 2 echoes of the ultrasound are received, one after 0.09 seconds coming from the shell of the fish, and the other after 0.12 seconds coming from the seabed. Now, if the seabed is 84 meters below the ultrasound transmitter and receiver, determine part A, the speed of the ultrasound, and part B, determine the wavelength of the ultrasound in water and also the depth of the shell of fish below the boat. So look at this. One thing that you're supposed to know is that we are talking about echoes. Echo is reflected sound. So the time that has been recorded here, after which echoes are received, that is the time taken for the light waves, not light sound, sorry, for the sound wave to travel from the transmitter to the shore of the fish and also to the seabed, respectively. So the distance given is the seabed from the transmitter, meaning that if we have distance as 84 meters, and we are also having the time taken to the seabed, it's 0.12 seconds. Now, for us to get speed, we need to talk about, you see, the distance traveled within this time is twice the distance provided. So because generally speed equals to distance out of time. This is the basic relationship between the three quantities: speed, time, and distance. Distance over time. Therefore, here we are saying the speed will be given by within 0.12 seconds. This distance is covered twice. This distance is covered twice. So within 0.12 seconds, we've covered a distance of 84 times 2, because the sound has to go to the seabed, get reflected, and bounce back to the receiver. And then the time is recorded. So what are we getting from this? We can compute from our calculators 1400 meters per second. Now this is the speed of sound in the water. Part 2. We told to determine the wavelength of the ultrasound waves in water. Wavelength of the ultrasounds in water. We know very well that V, which is velocity, is given by F times lambda. Now, in this formula, lambda is the wavelength, F is the frequency, V is the speed. Can we substitute 1400? Is it 1400 or 14,000? 1400 equals to frequency 60,000 hertz. That is the value that we talked about at this point. This is now multiplied by a known lambda. So to remain with the, we have to divide by 2, by 60,000 both sides. Yeah, you divide by 60,000. So from this, we are getting a distance. We're getting a distance which is equivalent to 0.02333 meters. Yeah, wavelength is a distance, and it is usually given in meters. We can also write this in standard form, which is not a must. 2.333 times 10 to the power of -2 meters. Then part C, the depth of the shore of fish below the boat. You see now, we have the time taken for the sound to go and get reflected by the shore of the fish. The time recorded there is 0.09 seconds. Then the speed has already been computed in part A in meters per seconds. So for us to get distance, we're supposed to talk about speed times time. We're just changing the subject of the formula. Speed equals to distance over time. So distance shall be speed multiplied by time. Now, in this case, there is something that I want you to understand before we substitute. The time recorded here is the time that covered twice the distance. So we can say twice the distance equals to the speed and the time taken. So that, for us to get the distance now, we shall talk about this expression out of 2. Yeah, because the time recorded covered twice the distance. So we have to divide by 2 so that we get the exact distance. I can compute that very quickly. I'm getting exactly 63 meters. 63 meters. So that is the distance. That's a very good question. A very good question. And this is a question from sound. You know, sound is a special type of a wave, and it is in Form 2 physics. So that is something that you're supposed to understand very well. Number 4, if you're getting something, please type, I am learning. Let us also know where you're learning from. Please remember our hashtag, I am learning. Yeah, that way. Number 4, the diagram below shows a magnet attracting an object. So the object is here. It means it's a magnetic material for it to be attracted by the magnet. North, south, we can see the poles there. Then here comes the question now. Here comes the question. Give a reason why the object is attracted to one end of the magnet and not the central part. This object, if it's let to attach itself freely, it will be found to be attached at the poles, either the north or the south. So we say this is because the strength of a magnet is stronger at the poles. The strength of a magnet is stronger at the poles. At the poles than alongside the bar. You can just say that. Than alongside the bar. Alongside the bar, the magnet bar. This is because we have more magnetic field lines at the poles, which make the magnets to be very strong at the poles, unlike at the central part. The same experiment can be done by dipping a magnet in a container that has what we call ion filings, yeah, or very many small pins, very light. And you find the ion filings are attaching themselves, a lot of them at the poles at the end of the experiment, a lot of them at the poles, but now very few along the bar, showing that at the poles, we have very strong attraction forces. Part B of the same question. This is a magnets, the first topic in Form 2 physics. You remember that, eh? Now explain why attraction is not considered as a surest way for testing polarity. The same question can be asked in a different way, where you'll be told to explain why repulsion is the surest. So repulsion is the surest method. Attraction is not. The reason why it is so is because attraction occurs between two unlike poles and between a magnet and a magnetic material. So when attraction occurs, it can be because whatever has been attracted is unlike pole from another magnet, or it might occur because the material that you're bringing is just a magnetic material. For example, here, you know, attraction can occur because this is a north. You see, it has been brought at south. So maybe the attraction is because this is another north, or it might just be attracted there because this is a magnetic material. So you may not know why attraction has occurred, but whenever repulsion occurs, there is no other option apart from knowing that whatever has been brought is a magnet, and that particular pole is very opposite or unlike to the one being repelled. So we say repulsion occurs only between like poles of magnets. So whenever you see repulsion and there is a permanent magnet that you already had labeled the poles, then you know automatically the pole being repelled can be determined by considering the pole repelling it. So repulsion is the surest method of testing for polarity. If you're getting something from magnets, please type I am learning. This is a very good paper, and before the end of it, you shall get something. Believe you me, trust me that you shall learn something. So we can proceed to number 5. I can see this is on Electrostatics 1. That is Form 1 physics. Electrostatics 1. I've said for you to handle a paper successfully, please remember to place every question in its context before you start responding. Understand where a question is coming from. From that perspective, you'll be able to analyze the examiner's intention, and you will end up submitting the right answers. A negatively charged rod is brought near the cap of a lightly charged electroscope. Underline lightly charged electroscope. The leaf fast drops or fast decreases in divergence. But as the rod gets nearer, it diverges. Part A. State the charge on the rod. Now, as long as there is some decrease in divergence, then it means as you started bringing the negative rod, there was some attraction. Something was attracted. Therefore, the rod is slightly positively charged. So there is positive charge. State the charge on the electroscope. It was a positive charge. That is why there was some attraction. You know there is this. Let me draw for you. There is the cap. There is the metal bar or the metal plate. Then there is a leaf here, the gold leaf. Now, when you bring the negative rod here, it's good for you to know that because it was slightly charged, those charges will get attracted. And as they get attracted, if they were positive, when they get attracted, it means both the leaf, the gold leaf, and also the plate, they will lose some positive charges. You know, there was divergence because with positives here on the plate and positives at the leaf being like, they repelled one another. So when they got attracted by the negatively charged rod, there was some decrease. But because they were very few, it means they will suddenly get neutralized. And now, this plate now, as you continue now bringing, the rod closer, which is negatively charged. Now more electrons will be pushed down. Yeah, more electrons will be pushed down. So you can say when the negatively rod, on the explanation now, when the negative rod, the negatively charged rod is brought close, the positive charges are attracted. This is what reduces divergence, reducing divergence of the leaf. The leaf divergence is decreased. So as the rod is brought closer, as it is brought closer, since it is negative and the positives which were lightly charging the electroscope could not fully neutralize the charged rod. Now we're saying more electrons are pushed down. Remember, it's now not charged. So more electrons will be pushed. More electrons will be pushed down, increasing the divergence. Increasing the divergence at the leaf, or the leaf divergence is increased. Remember, divergence is increasing simply because divergence is increasing with a reason. It is increasing because when negatives now from the rod are being pushed down, the plate will be negative, the leaf will be negative, and the more electrons are being added to either of them, because they are like poles, they attract one another. So the charges on the plate will repel the charges on the leaf, and there will be some divergence due to the reflection. Looking at number 6 now. Looking at number 6, ladies and gentlemen, distinguish between longitudinal and transverse waves. Okay, longitudinal waves and transverse waves can be distinguished in many ways, but basically we differentiate them by considering the behavior of movement of particles. So we say longitudinal wave is a wave in which, let me use the space here. In longitudinal waves, particles move parallel to the wave motion, while in transverse waves, the particles move perpendicular. This moves perpendicular to the wave motion. There are some other differences. For example, you can say that longitudinal waves are characterized by what you call rarefactions alternating with compressions, while a transverse wave comprises of crests alternating with troughs. Crests alternating with troughs. This is a transverse wave. Crest, the topmost, trough, the bottommost particle can go. So we say in a transverse wave is characterized by crests and troughs, while what we call longitudinal waves, they are characterized by refractions followed by compressions. The figure below shows how sound is propagated on the diagram part 1. On the diagram part 1, identify the regions of refractions and the regions of compressions. So compressions are regions of high pressure regions. And in such cases, the particles are closer to one another. So this is a compression. These are compressions. Then when they start spacing out up to that point, this is a region of a rarefaction, a region of low pressure. That's a rarefaction. So we have rarefactions alternating with compressions. Then on the same diagram, identify, okay, show one wavelength. So one wavelength should be the distance showing a complete compression and a complete rarefaction. That gives, or the distance between a successive compression and a rarefaction, this one, up to that point. So that will be called, that way. So that is a complete wavelength. A complete wavelength. You can also start from a rarefaction and go until you are at the end of a compression. So it can still be that distance. Yeah. It can still be there from the start. Sorry for that. I hope you are getting us. I hope we are clear. Yes, that is it. If you're getting something from waves 1, that is again from 2 physics, type I am learning. Let us know where you are learning from. Please subscribe to this lesson and remember to share the link. Remember to share the link. We are checking number 7. Okay. You are provided with 3 identical cardboards with holes at the center, candle, and a source of light. Describe an experiment to demonstrate that light travels in a straight line. First, you are supposed to arrange the cardboards. Arrange the cardboards. Such that the holes align. And place the candle, of course a lit one, a source of light. The lit candle, lit candle at one end. Then observe the light. Observe the light from the other end. After that, displace displace one cardboard. Displace one cardboard and observe again. And observe again. So you displace one card such that now the hole is not in line with the other holes, then you make the observation again. This time round, the light is not visible, is not seen, indicating that light travels on a straight line. Light travels on a straight line. Yeah, I know this is a very famous experiment, and in one way or another, you've even conducted it practically in your class. You have even practiced it in the class. Let us check. This question. Now we are having a number 8. Trace the ray of light when the mirror is inclined as shown below, showing all the angles. Okay, we can see the ray of light is perpendicular. But the mirror is inclined. So this is the mirror. The mirror is at an angle. So mathematically, you can see that because this is 15 and this is perpendicular 90, this is then 75. If that is 75, we can start by drawing a normal at the point, where this perpendicular, where this normal, a normal like that. This is normal. A normal where the ray of light is making contact. Yeah, where it is making contact with the mirror. Then from there now, you see this is 90. That is 90. So it means we're supposed to have another angle. And for your information, because there is this intersection of the ray of light and also, look at this. Let me just redo that. There is this intersection of the ray of light. Then it means this angle is vertically opposite. It's supposed to be 75 like that. Yeah, if you have a 75 there, then vertically opposite, there is a 75. Meaning that when we draw our normal now, which is supposed to be perpendicular at the point of incidence, then this angle is 15 degrees. And we know very well with plane mirrors, the angle of refraction is usually, actually not refraction, reflection, bouncing back of light. So the light bounces back, making an echo that is equal to the angle. So we can draw now a ray which is equal to the first one. So the reflected one will go away also through 15. Yeah, 15 degrees like that. So the reflected ray should also be 15. So that's a good question in number 8. It's a very good question in number 8. Then we check number 9. Remember, we were still in section A, and we shall handle section B as long as the stream can continue hosting you. So please remember to subscribe as we continue learning. Remember to share. Remember to invite a friend to these powerful lessons. Explain why, in number 9, gamma rays are considered ionizing radiation while radio waves are not. This is about what we call the electromagnetic spectrum. For rays or radiations to ionize, they must be having what we call ionization energy. So radiations will have different ionization depending on their position in the spectrum. You know that, eh? So there are 7 main components of the spectrum, and that is what we're going to list. Then we respond to the question. Sorry, I know I'm diverting your attention. Some of you are after just responding to the question. 1, 2, 3, 4, 5, 6, 7. So if we talk about increasing frequency, remember we talk about R, M, I, U, X, and G. That's how they follow one another. There are some acronyms that are used to make sure that people memorize how they start from the one with the least frequency to the one that has highest frequency. Roasted maize is very unusual Xmas gift. Roast maize is very unusual Xmas gift. That one will give you the order of increasing frequencies in the electromagnetic spectrum. This is for radio waves, microwaves, infrared, visible light, ultraviolet. Then we have X-rays and gamma rays. So when you look at the position of radio waves, which has the least frequency, and you look at the position of gamma rays, you know, gamma rays are written like this. They have the highest frequency. Then I take you back to the energy equation. The energy that they possess is given by a constant, Planck's constant, times the frequency of the respective radiation. Now you can see very clearly that the amount of energy contained in a particular radiation is directly proportional to the frequency that it has. And now according to the order, you can see that gamma rays have the highest frequency, which means they contain the highest energy, which means they are the most ionizing radiations. Therefore, gamma radiations ionize air particles or anything. Gamma radiation or rays have the highest frequency, which gives them a lot of energy. It is also this energy that makes them to be having the highest penetration power and such other things. A lot of energy, hence able to ionize. They are able to ionize. On the other side, radio waves. On the other side, radio waves have the least frequency, meaning that they can rarely ionize. So they have very little power to ionize. Ionization energy, they can't provide. As we transition to the section B, allow me to remind those who are joining us late that we have programs over the holiday via Google Meet, which are very interactive, very transformative, and also impactful. You can reach out before or on 13th because we are doing it for 2 weeks, all the way to the 24th. We shall be doing physics, mathematics, chemistry, Kiswahili, English, basically the sciences, the languages, and mathematics. We invite you cordially. Remember also to invite your brothers in junior school. We have their schedule. Every level is being handled on its own. So don't think that there will be any confusion. You are being mixed by a learner of a lower level or such a thing. Not really. Not really. So please be sure that everybody is being given quality respectively. So kindly enroll to our classes. Very affordable also. Running from 9 a.m. to 1 p.m. So those are enough hours. Please enroll and enjoy the best services at Shifting Grades Online School. Number 10, define period as used in waves and state its SI unit. Now, what you call about period, this is the time taken to make a complete oscillation, a complete cycle. SI unit is the second. Remember, period is time, and time is measured in second. So that is it. 2 marks. Stating second and defining period. There are many other characteristics of waves and terms which require your understanding. So please don't let yourself down by staying without visiting your Form 2 book where waves are introduced. We check part B of the same question. The sketch of a displacement time graph of a wave traveling at 160 meters per second. Now the wave takes 0.5 seconds to move from point A to point B. Determine. You have several parts. You can look at part 1. The amplitude of the wave. Amplitude is the highest point where a wave can move, or the lowest. And when you look at the lowest, you can consider a trough here. So it's giving us 5 units on the lower side. And also upwards, there are 5 units, and these are millimeters. So we talk about 5 millimeters, which can be converted by dividing by 1,000 to 0.005 meters, because the SI unit of amplitude, being a distance, is meters. So 0.05 meters is the amplitude. The highest level particles can move to, or the lowest level they can also move to. So when you consider the lower side of the y-axis, you ensure that you just pick the absolute value. You can't have an amplitude of -5. Ladies and gentlemen, amplitude cannot be negative. If you read the maximum distance on the lower side, then you pick absolute value. I hope I'm clear in that. If you've learned something, type I am learning. Then we check we can check part 2. The speed of the wave is also supposed to be determined. When I try to look at the question, I am sure speed has been given. Yeah, speed has been given. So maybe, and from this, we have time here. That means frequency can also be determined. So please allow me change this question to determine the wavelength of the wave. Generally, velocity v is given by f times the wavelength. So to determine the wave, we already have a frequency can be determined. Let's check the total time of 0.5 seconds here. How many oscillations are being covered here? Remember, a wavelength is a combination of a complete crest and a trough. So the whole of this plus the whole of this, that gives us the first complete cycle, 1. Then we flow again 2. We flow again 3. So 3 cycles are taking 0.5. 3 cycles, 0.5. Okay. So 3 wavelengths, 0.5 seconds. What about? Okay, when I get 1 wavelength, I'll get periodic time. Allow me, instead of getting periodic time, I'll ask ourselves, what about the oscillations made in 1 second? Because the number of oscillation per unit time gives us frequency. Definition of frequency is the number of complete oscillations made in 1 second. So, if 0.5 seconds, there are 3 oscillations made. What about in 1 complete second? To be 1 times 3 over 0.5. Is this 6? 6. So it is now the frequency, which is 6 hertz. Yeah, 6 hertz. So the frequency is 6 hertz. 160 equals to frequency times lambda. To remain with lambda, our wavelength, we can now divide 160 divided by 6, giving us 26.67. Yeah, that is now what it means. That is exactly what it means. It's a very good question anyway. A very, very good question. If you're getting something on the wave equation, please type I am learning. That is if you're learning. Yeah? Now, a student observed a wave in a swimming pool crossing a boundary at an angle as shown in the diagram below. You can see the boundary is at an angle. Then it is moving. The waves are moving from a shallow region to a deep region. One thing that we should know is that as waves move from a shallow region to a deep region, we say that frequency remains constant because the waves are being generated from a common point. Yeah. Being generated from a common point. Therefore, we are saying frequency remains constant. But now as the waves transition to a deeper region, speed increases. Now, when speed increases, look at this. Speed increases, this one has increased. This one remains constant because they are being, frequency is the rate at which they are being produced. The producer of the wave is just the same. They're being generated from one point. So there's no variation on the frequency. Then automatically, to catch up with the increased speed in the deeper region, now wavelength has to increase also. Therefore, one thing that is supposed to be very sure is that because velocity shall increase, then as the waves transition, the wavelength will also increase. So complete the diagram to show how the plane waves will emerge after crossing the boundary. After crossing the boundary, we shall talk of, let me draw a normal at this point. This is a reflection of waves. You can draw a normal at that point. Then the wave now shall be reflected. It shall be reflected. The wave shall be reflected in a direction like that. And after the reflection now, you can be sure from one wave to the other, we shall have increased wavelengths. Increased wavelengths. The wavelengths will have increased. So that is it. You show the increment in the waves. The increment in the waves. That is now reflection. If you're getting something, please type, I am learning. I am learning. Part D. Now, the diagram below shows two speakers placed parallel to each other. You can see them. The speakers are connected to the same audio frequency generator. The same audio frequency generator. Use it to answer the questions that follow. Part A, state the reason why the two speakers are connected to the same audio frequency. And this is to ensure that there is a coherency, or rather, for the waves to be coherent, for a coherent source of sound to produce or to hover a coherent source of sound, or rather you can say for coherency. You say for coherency. Remember, even when it is sources of light, they are supposed to be having coherency. What you'll be talking about here is what you call there are many properties of waves. So there is the merging of waves. There is to form bigger waves, to form smaller waves. Some other times we have just dealt with refraction. There is refraction and reflection of waves. There is what we call a diffraction. We shall see it as we continue progressing. There is what we call interference. You see, interference now is the merging of waves. So speaker A is producing sound, speaker B producing sound. So we call that one, when the sounds now intertwine, when they meet, we call it now interference. Call it interference. So that is something you're supposed to know. The properties are very many. Properties surrounding waves are very many. And that is why you're supposed to know the behavior of waves. In many occasions. In many, many occasions. So the reason why they are supposed to be connected is to offer coherence. Now state and explain the observation. If an observer walks along XY, the observer will be experiencing loud sound alternating with soft sound. Those will be the experiences. Loud sound alternating with soft sound. So loud sound alternating alternating with soft sound. Then when you start, that is the observation. When you start explaining, you say the loud sound is due to constructive interference, while the soft sound is due to destructive interference. Destructive interference. So there is interference. When interference is constructive, you will hear a loud sound. When it is destructive, a soft sound. So those will be the observations. You can check part E of the same. Now the figure below shows wave fronts approaching narrow opening. Just look at that narrow opening. Now in this case, we talk about what? Diffraction. The ability of waves to curve as it moves beyond openings or beyond obstacles. We call it diffraction. Complete the diagram to show the appearance of the wave fronts after crossing the opening. So when you look at the size of the wavelengths, distance from one wavefront to the other, we call them, those are the wavelengths. So when you consider the wavelengths and you consider the size of the aperture, the slit, the opening, then it is clear that the opening is smaller. And when it is smaller, there is what we call diffraction. Diffraction happens, the curving. So they shall emerge as circular waves. But now as they become circular, one thing that you're supposed to know is that the wavelength is usually maintained during diffraction. Wavelength is maintained. So this distance, which is approximately 0.7 centimeters, should be kept constant. From one wavelength to another, the distance is maintained. Even after they have become circular waves, they proceed with the same wavelength. I'm trying to maintain the distance, so make sure you maintain the distance like that. So that's how they behave. Remember, you can be given the same wave fronts, the same wave fronts. Then you are told they approach an opening which is bigger, an opening which is bigger than an opening which is bigger, like that. So the slit, you can see it's bigger. The slit is, yes. So in this case, you can see very well that the slit is bigger than the wavelengths. Is the wavelengths. It is now smaller. So the waves will be slightly diffracted. So they don't become circular in such cases. So it is not a narrow, it's now a wide opening in this case, because it can be a different question. They continue being plane waves. They continue being plane waves, but now with a slight curving at the ends, like that. Remember, because it is diffraction, again, wavelength is maintained. So wavelength is not changing, but the slight curving is experienced at the ends of the waves. Slight curvings. Just a slight curving, but they don't become circular waves. They don't become circular waves. So that is it. So sometimes it can be a narrow opening where they become circular, as it is in this question. Some other times it might be a wide opening where they remain plane waves, but with a slight curving at the ends, the slight curving at the ends. Number 11, ladies and gentlemen, number 11. The figure below shows current through a loop. You can see current through a loop. Current is through here. Current is also through here, okay. Through a loop like that. You can see a source of power. Then you're told to draw the magnetic field pattern and indicate the direction of the field. Indicate the direction of the field. So what you need to know is that this is the positive terminal on the batteries, negative terminal. So when you complete the switch, you shall have current flowing through this direction, and it shall come back through that, yeah, like that. So that is the flow of current. So as the current flows upwards, you are supposed to know that some magnetism, a magnetic field will be generated. A magnetic field will be generated, and it will give us a certain force. Therefore, at that point now, we should know that there will be field lines created. You know, when current flows according to the magnetic effect of an electric current, that is still Form 2 physics. According to magnetic effect of an electric current, when current flows, it generates magnetism. And in Form 4, in electromagnetic induction, we say when magnetism is applied on a conductor, current can also be generated. So that's why we have a branch of physics called electricity and magnetism, electromagnetism, because the flow of current generates magnetism, and a magnetic field can also induces current actually. So magnetic field induces current, and current flowing induces magnetism. They cause one another. So now during the flow of the current, we shall have some magnetic loops now generated at this point, and they shall be to that direction like that. So on the other side now, it will be the opposite, because it is now current is flowing like this. So now at this point, direction now will be in this direction, in the opposite direction compared to the other one. Yeah, like that. So when you check now, when you check the flow of this, magnetism now, the force that will be induced shall move upwards now. So this is where the force will be. So you show the force like that. This should be part B. I think they are part B, not C. Part B, because it's the same question. 11 part B. With 11B, we are told that the figure below shows a rectangular plane coil ABCD inside a magnetic field. So a coil inside a magnetic field now. I think this is what I was trying to tell you. On the diagram, indicate the rotation of the coil. You know, the rotation of the coil will happen because we are already having a magnetic field. We have a north and a south. So magnetism is already moving from the north to the south. There is already magnetism here. Field lines are moving from the north to the south. Then now, when you close here, this is positive, this is negative. So there is current again flowing here. Current is flowing in such a direction. Therefore, according to the Fleming's left-hand rule, when you consider the side where there is S, then you can see first finger showing current, first finger, current. First finger showing current. Then we can talk about no, actually it should be, sorry, it should be second. This is the second finger. If you hold your left hand such that the second finger is pointing the direction of current, and also you will have now the first finger. I don't know how you are going now to hold your fingers, showing us the direction of the magnetic field. Then automatically the thumb, which at this point now, you know, by the time the first finger is showing us the direction of the field, and the second one shows us the direction of the current, then the thumb will automatically be facing upwards. Yeah, your thumb will be automatically facing upwards. So you can try that experiment. Try that experiment using your hand. I'm sorry, I'm not on a video that can be recorded, but it can be very okay actually. It can be very okay to show you that this is the thumb pointing upwards. the first finger showing direction of the magnetic field. Then this is the second finger showing us direction of the current. Then automatically we can say that it will move towards the force, which is upwards. So that is the movement of the movement of the coil, and automatically on this side now it has to go downwards. So the movement of the coil shall be upwards. That is the coil movement upwards, where the thumb is pointing. Where the thumb is pointing. Part B, or part 2, explain why the coil begins to turn. I think I've already explained that. The interaction of the two fields, an electric field and a magnetic field, will result to a force which is upward. So due to the interaction between magnetic field and the magnetic and the current, due to interaction between magnetic field, you can say that due to interaction between the magnetic field. You know, we have two magnetics now. Magnetic field on the permanent, magnetic field on the permanent magnet, and the magnetic field of the electromagnet. We have two magnets here. An electromagnet, because of the current that is flowing on the coil, there is some electromagnetism. So an electromagnet is produced, and this magnet is having a field which interacts with the field of the permanent magnet, a force is produced. So it is now this force which will make the coil to move in the direction which has been identified using the left-hand rule, Fleming's left-hand rule. Roman 3. You can check Roman 3 of the same question. Name the parts labeled X and Y. X is here. You can see the arrows pointing X. That is the carbon brushes. Then when you look at Y, trying to look at Y, I think this is a mislabeling. That is A. So allow me have X and Y. This is Y, not A, sorry. So that A now, that is the commutator, or rather the split ring. You can see it is split. The split ring. So-called the commutator. Like that. So that is the name. Then one way of increasing the speed of the electric motor. There are many ways. The examiner demands only one. You can increase the magnitude of the current. Increase the magnitude of the current. You can also increase the strength of the magnet. We use a stronger magnet. Sorry. I hope you can get us well. Sorry for that interference. Use a stronger, magnet. There are very many ways. You can even increase the number of coils. like that. Increase the number of coils. Yeah, you get man mark from any of those points. From any of those points, you get a mark. There is a very good question here on current electricity. That is what we shall be discussing next. These are very good questions. Let's check. Let's check what we have here. A student. Yeah. A student wanted to minimize electrical energy consumed in their class by the lighting circuit without reducing the number of bulbs. State one way in which they could do it. You can ensure that the electricity consumed is less by arranging the bulbs in parallel. Arranging the bulbs in parallel, arranging bulbs in parallel have many advantages. Apart from minimizing electrical consumption, there are other advantages of ensuring that the lamps are in a parallel connection. Part B, distinguish between electromotive force of a cell and the potential difference across a resistor. Okay, we know that when we talk about electromotive force, EMF, or capital E, is the voltage across a cell. Yeah, the ends of a cell, that is, when the cell is not supplying electricity. When the cell is not supplying current, or rather, when it is in an open circuit, when it is not doing anything, it is in an open circuit. But when we get to potential difference, which is a V, potential difference, or simply V, say this is capital E, is the potential difference. This is the potential difference, or simply voltage, when the cell is supplying current or is in a closed circuit. When it is in a closed circuit, it is now supplying current, and it is usually said that, or it is practically proven that potential difference is usually now lesser. Actually, we call it a terminal. Yeah, terminal voltage. Terminal voltage. Terminal voltage is usually slightly different or slightly smaller than EMF. EMF is the voltage before the cell starts function. If you're getting something, please type I am learning. Part C of the same question. Part C of the same question. We are told that 3 resistors are connected in series across a 75-volt potential difference. Just as you can see. Then R1 is 170, R2 190. You can see R3 is unknown. The potential difference across R3 is also given as 21 volts. Yeah, 21 volts. Find the current in the circuit. Total current in the circuit can be found. This is what I want you to know, ladies and gentlemen, that these particular resistors are in series. So total resistance, or rather effective resistance, is given by addition of the respective resistors, resistor 1, resistor 2, or the way to the last one as long as arrangement is series. Then from there, we can now agree that the total resistance in this particular connection is given by R1, 170, R2, 190, R3, unknown, because they are only three, like that. That is total resistance. Again, we can say that according to what we call the Ohm's law, we say that V, voltage, equals to IR, current times resistance. So the total voltage here, which is 75, equals to total current unknown multiplied by total resistance in the connection, 170 plus 190 plus unknown R3, like that. That's an equation. Something else that we're supposed to know is that when components are in series, just like these particular resistors, the current flowing through them is the same. So the current through them, even if potential difference at each is different, we shall have the same total current shall flow across them. Therefore, how do we get current? Okay, the current is high. Letter I can also be used because it is the same current flowing through them. So if we let this one to be our equation 1, then can we talk about equation 2, whereby we will say, according to R3, the voltage there of 21 equals to current, the same I, multiplied by the resistance that is unknown, R3, like that. According to the same equation, now we consider R3 alone, whereby we have the voltage there, but we don't have resistance and current. So we have two equations which have two unknowns. So from this, we can say, this is our second equation. The value of R3 can now be described in terms of current, and R3 is equal to 21 out of current I. You divide through by current. So now we rewrite equation 1 and say 75 equals to current into 170 plus 190 plus, instead of R3, 21 over current. 21 over current. Now, when we open brackets, it shall be 75 equals to 170 current plus 190 current plus 21, because the current now will cancel. Remember, at this point, current is the divider. Can we now talk of grouping terms, whereby we will have 75 and we subtract 21. This is 54, being equal to 170 and 190 should be added to give us 360, the value of current. How shall we remain with the value of current? By taking 54 over 360, giving us 0.15 amperes. 0.15 amperes. So that is the current. It's a very technical question whereby a student is supposed to understand how to compute current, how to compute voltage, how to compute resistance. Find also the value of resistance R. You see, the value of resistance R has already been expressed here. So R3 equals to 21 out of current, and current has been computed now. So when you compute this, you get exactly 140 because it is current. Because it is resistance, the SI unit is ohms. That is the symbol of ohms. Yeah, that is the symbol of ohms. Then we can check part D on current electricity. Now in part D, we told that the setup below can be used to experimentally demonstrate heating effect of an electric current in the lab. So you can see paraffin, you can see a coil, you can see a stirrer, a thermometer. Then you can see a circuit here, a circuit diagram for the supply of the electricity. Now state and explain the reason why the coil is highly coiled. It is highly coiled to ensure that it increases resistance, because the longer it will be, the higher the resistance. So to increase resistance, this in turn increases the heating effect. The heating effect of the current. The heating effect of the current. When resistance increases, then heating effect of the current shall also be increased. Now, in part 2, we are told to name the electrical property the material possesses to suit it as the coil. So the coil should be having high resistance. That is the only property. It should be a material of high resistance, like that. It should be a material of high resistance, like that. Then in number 13 now, or if you're getting something from current electricity, kindly type I am learning. Then we check number 13 together. Now define the term principal focus of a concave mirror. This is very specific. It is a mirror, not a lens, and it is concave, not convex. So principal focus, or the focal point, can also be called the focal point. It's good you know that. It's also called the focal point of the mirror. This is the point. It is the point where rays parallel and close to the principal axis converge after reflection. After reflection by the mirror. After reflection by the mirror, rays that are close and parallel to the principal axis will usually converge. Underline the word converge. No wonder the same type of a mirror is called, the same type of a mirror is called a converging mirror. Like that. We can check part B of the same question. In part B, we are told that the diagram below shows a ray diagram with object O placed in front of the concave mirror. Complete the diagram to locate the position of the image. You're supposed to know the basic rays and how they behave after reflection by mirrors and also by lenses. Supposed to be very good in what you call geometric optics, the behavior of light as it traverses different media. A ray, which is close and parallel to the principal axis, for this type of a mirror, will be reflected away after hitting the mirror through the principal focus, capital F, like that. That is how the ray shall behave. That is now the first ray. Now, we can come up with another ray. We usually say a ray that is through C. Once it reaches the mirror, it gets reflected through the same path. So a ray through C, gets reflected through the same path. a ray which is going to see shall be reflected through the same path. So when you look at these two rays, they are not likely to intersect anywhere in front of the mirror. But when you project them virtually behind the mirror, they are likely to meet and form a virtual image, which is upright and magnified. So you just extend yeah, you can see they're meeting somewhere. So now you can extend your principal axis. You can extend the principal axis like that. Then now after the rays have intersected up there, our image is now upright. It is virtual, so you don't use complete lines. That is where the image is. This is our object. So that is the image behind the mirror, magnified and virtual in nature. That's how you complete the rays. Some other times you'll be told to complete the rays, then you proceed to state properties. You should be able to interpret the diagram. We can continue interpreting diagrams, ladies and gentlemen. Let us continue interpreting the diagram. Part 3. The figure below shows a graph of image distance, that is a V against object distance, small letter u, for a concave mirror, just as you can see. From the graph, part 1, determine the focal length of the mirror. Determine the focal length of the mirror. You see there are many coordinates here, and you shall allow me pick any coordinate here, like when u equals to 10, v equals to 30 at this coordinate. You can see down there we got 10, and across here we are having 30, like that. So we know that the mirror formula says that 1 over f equals to 1 over v plus 1 over u. Therefore, using one coordinate, you can say 1 over 10 plus 1 over 20 equals to 1 over f. So 1 over f is equal to, we add 1 over 10 and 1 over 20. No, that's 30, sorry. This is 30 and 10. So 1 over 30. Sorry, in that substitution. And also in my calculator, I changed that. We get 2 over 15. So if the reciprocal of f equals to 2 over 15, then f shall be the reciprocal, 15 over 2. So this gives us 7.5, which is 7.5 centimeters. 7.5 centimeters, like that. We can check the next question. We are having a part 2. Now in part 2, we are told that we determine the magnification produced by the mirror when the object distance is 8.5. We know that magnification is given by V out of U, image distance out of object distance. So the magnification shall be V, unknown V out of U 8.5. So we read the value of V when U equals to 8.5. So at 8.5, we get to the graph. 8.5 This is a 5, 10. So 6, 7, 8, 9, 10. So 8.5 is the mid there. At the mid here. And now we read across there. Across, we check the value of B, which is here. 30, so 32, 34, 36, 38. 38. Then you divide 38, divide by 3 point, divide by 8.5. This is giving us exactly 4.47. That is the magnification. Then part B, which is on application, we are taught to state why convex mirrors are preferred to plane mirrors for use as driving mirrors. So convex mirrors have what we call a wide field of view. Convex mirrors have a wide field of view. A wide field of view that gives them an upper hand when it comes to driving mirrors. If you're getting something from reflection at curved surfaces, that is from 2 physics, please type I am learning. Yeah, type I am learning. And we continue learning. Is this the last question? Not really. There are more questions. There are more questions. So let us proceed. Let us proceed until we cover the paper. Number 14, ladies and gentlemen, state the Faraday's law of electromagnetic induction. Now, the Faraday's law states that the magnitude of the induced EMF is directly proportional. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The rate of change of magnetic flux linkage. Yeah, flux linkage like that. Part B. Now the figure below shows 2 free ends of a coil connected to a galvanometer. When the north pole of a magnet is moved towards the coil, part A, identify the polarity. Identify the polarity of A. Identify the polarity of A. One thing that you're supposed to know is that there will be some current. There'll be some current that will be flowing here. And for that reason, you're supposed to know that if the direction of the force causing the magnetism and also the current is in this direction, then we are supposed to know that according to let me use several laws to identify. You know, current will be flowing this way. Current will be flowing. Galvanometer will be moving on the opposite direction. So the current produced is usually opposite to the direction of the change trying to cause it. That is according to Lenz to the lens is low, the EMF that is produced will be trying to oppose the change that causes it, meaning that this is how current shall be flowing now. So in case we hold with our right hand, this particular, in case we hold this particular core, in case you hold it such that, using your right hand, such that the fingers are pointing the direction of the flow of current as you can see it, then the north pole will show you the north pole. The north pole is going to be shown using your thumb. The north pole is going to be shown using your thumb. So this is a north pole. Okay, sorry. When you hold, just a minute, when you hold such that, using your right hand, the direction of current is now shown using your fingers. Then the north pole will be shown using your right hand, So this is a north pole, very true. We call it the right hand grip rule. Right hand grip rule. Now, according to the right hand grip rule, please now observe keenly. Now, when I hold such that my fingers are now in the direction of the current, as you can see, then we shall have my thumb pointing to the north. Therefore, I have a north produced at end B. And if B is a north, we wanted to identify A. So A is not a north now, it's a south. Sorry for that, A is now a south. So I've used right-hand grip rule to show that B is a north. Now, if B is a north, then automatically A is a south. That is the magnetism produced there. But basically, I said, according to the Lenz's law, when you bring in the magnet, the permanent magnet, now the EMF produced shall be having a force which tries to oppose the change that is causing it, meaning that the flow will be in the opposite direction. So this is how the galvanometer will deflect. That is why I've already answered part 2. Answering part 2 is what has made me to answer part 1 very well. Now explain why. Explain what is observed when the magnet is held stationary inside the coil. No deflection. No deflection on the galvanometer. Galvanometer. No deflection on the galvanometer. There is a reason why there is no deflection at the galvanometer, and this is what I want to explain. First, that is the observation. You see, for there to be an induced EMF and hence a flow of current, which is now detected by the galvanometer, there should be magnetic flux linkage. So we say there is no magnetic flux linkage. You see, there is magnetic flux linkage when either the coil is moving to the magnet or the magnet is moving to the coil. There must be a relative motion, or it could be the magnet is here, then we have the coil itself moving. And remember, it can be the coil to the magnet or the magnet to the coil, but at least there should be some magnet. And remember, the current produced is directly proportional to the rate of magnetic flux linkage, according to Faraday's law, whereby the faster you move the magnet in the coil, the greater or the faster the rate of magnetic flux linkage, and hence the more the EMF, and hence the greater the current produced. So without a relative motion, there is no linkage. There's no magnetic flux linkage. So when you hold the magnet stationary, and also the coil is also stationary, there shall be no linkage and hence no current, meaning that the galvanometer shall not deflect. The galvanometer shall not deflect. Part C. A transformer has a primary coil of 1,000 turns and a secondary coil of 50 turns. Part 1. Identify the type of the transformer. You see, the number of turns are the ones that will induce an EMF which is greater or lesser depending on the stationary. So at the input we have 1,000, but at the output they are 50. This means this is a step down. This is a step down transformer. A step down transformer. If we add a smaller number on the primary but a bigger number on the secondary, it would be a step up transformer. In part 2, if the primary coil is connected to 200 volts main supply, determine the secondary voltage, which is going to, of course, be smaller. So according to the transformer ratios or the turns ratios, transformer equations, we say the ratio of the number of turns in secondary over the number of turns in primary is the same as the ratio of voltage in secondary over voltage in primary. Substituting this, it shall be 50 over 100, no, 1,000 equals to the primary is connected or about the secondary, so 250 is here. So to remain with Vs alone, voltage at the secondary, we multiply by 250 both sides. So 50 by 250, then divide by 1,000. This is 12.5. No, it's, sorry. You know, the value that is given is 240, not 250. Sorry for that wrong substitution. 240, yeah. So when I'm multiplying 50 by 240 both sides, then over 1,000, I shall be getting exactly 12 volts. Exactly 12 volts, like that. Then there is a part 2, whereby we are told, given that the primary current is 0.96 and the secondary current is 12.8 amperes. Determine the efficiency of the transformer. Efficiency of a transformer is given by power output out of power input expressed as a percentage. How generally do we get power? Voltage times current. So power output is the power at the secondary. Power output at the secondary. So 12 is the voltage in the secondary, and current there is 12.8 out of power input, power at the primary. Voltage in the primary is 240, and current there is 0.96. Now we express this one as a percentage. 12 times 12.8 times 100 out of 240 by 0.96. This is giving us exactly 66 point. So I love it as 66.67%. So that is now the efficiency of the given transformer. That is the efficiency of the given transformer. It's my hope that I have computed properly. It's good from that side you even compute. Make sure you also compute. Yeah, it's good to also compute and let us know whether the calculations that we are doing here are up to date. It's good for you to confirm. Sometimes we can make mistakes. So about transformers, about electromagnetic induction, please confirm whether you are learning something by simply dropping a comment. Let us know whether you are learning. Then we check number 15 together from Electrostatics 2. Now state the property of electric field lines. Now electric field lines, one, they do not cross each other. They do not cross each other. They tend to, the direction, they move away from positive charge towards the negative. They move from positive and they enter negative charges. Negative charge. Yeah, they enter negative charge. We also know that they are many when the field is strong, and they are few when the field is weak. We know all that. So there are many properties. The examiner just wanted one. And we now check part B of this good question. Now the figure below shows the charges on part of the metal disc and a plastic block. We have positive and negative. On the figure, draw lines to show the shape and direction of electric field between the metal disc and the plastic. So we shall have the field lines moving from positive to the negative, just as we have said. So you just connect them directly from the positive to the negative, from the positive to the negative, and you indicate the direction very well. This direction is more important because without a direction, they are not even electric field lines. But with direction like that, you have shown where they are moving from. There are very many shapes from which electric field lines are moving from and to. Please ensure that you revisit them in your book 3, physics. Kindly visit them and know what happens there. We have answered that. Now let us check part C. The figure below shows a setup used to charge and discharge a capacitor. To charge and discharge. For charging, the contacts are closed at point X to connect the capacitor to the DC supply here. Yeah, to connect the capacitor to the DC supply like that. Let us now read. Explain how positive plate and negative plate of the capacitor acquire charges when the contact is closed at X. So when you close the contact at X here, like that, you see the capacitor is now connected to the supply. It's now connected to the supply the way it is connected now. Contact is made at X. Power supply is here. So the particular capacitor is able now to gain charges because negative charges flow from the negative terminal of the cell. Negative charges flow from the negative terminal of the cell, or rather the battery of the cell, to the negative plate, to the negative plate of the of the, not resistor, sorry, capacitor, of the capacitor. Then after that, after flowing to the negative plate of the capacitor, it is also very good for you to know that. I want to demonstrate first that step. From this, negatives are flowing to the negative. So negatives are coming on the negative plate like that. Then at this, these are electrons flowing. At the same time, remember when the capacitor had not been charged, it contained both charges. So through that, we shall say that negatives, because electrons are coming here, the electrons which were here will get repelled. So electrons shall move from the positive. So electrons again, or negative charges again, move. Negative charges again. Negative charges will move from the positive plate to, from the positive plate to the positive plate of the cell, to the positive plate of the cell. So the electrons that are being repelled will also move away to this side. So electrons are coming here. Electrons moved away from here, this direction. So by the fact that electrons have been repelled by the incoming electrons, now positives will remain here, because the positives remaining on the positive side are not in contact with the negative plate. There will be no neutralization. Therefore, equal positive and negative charges appear on the plate. Equal positive, equal positive, and negative charges appear on the plates. Yeah, so the point is that as after closing the contact here, electrons are flowing from the negative side. They enter the negative plate. While they are here, remember they are repelling away electrons. So electrons which were already there will be repelled through the other side. They get to the positive side of the cell. But now after positives have been remained here because they are being attracted by the positive, because there is no contact, they will not be neutralized. So the plates of the capacitor shall be having positives on the positive side and electrons on the negative side. That too. Yeah. Part 2 of part C. Now the capacitor becomes fully charged when the voltage across it is equal to that of the DC supply. Sketch the current time graph for the charging of the capacitor on the space provided below. So a sketch is usually made in a very simple way. Remember, this is also directly on the book. So this is how the curve is supposed to behave. Please confirm it in your notes. It's just like that. Then there is the last question, the last of the last. Now, a lightning arrestor consists of a thick copper rod with sharp spikes at the top, just as you can see. Sharp spikes at the top. Explain how these sharp points help protect a building during thunderstorm. It's so good for you to know that at sharp points, charges are usually highly concentrated. At sharp objects, they are highly concentrated. That is a mechanism which is being applied in this case. So we say when the negatively charged clouds, when the negatively, I think we can use all the space, yeah? When the negatively charged clouds pass over the arrestor, pass over the arrestor. They induce positive charges on the spikes. They induce positive charges on the spikes, the sharp spikes, and negative charges on the ground, and negative charges on the ground, and negative charges on the ground. Now, the negative charge on the clouds are attracted. The negative charges on the clouds are attracted. Negative charges in the clouds are attracted to the spike, to the spikes, and discharged, or rather neutralized and discharged by giving up their electrons. Giving up their electrons. By giving up their electrons. At the same time, positive ions are repelled upwards. At the same time, positive ions are repelled upwards. Remember, the spikes are positively charged, so positive ions are repelled upwards. Positive ions are repelled upwards. Sorry for that. They are repelled upwards. Sorry for this. They are repelled upwards. Let's continue. You can ignore that interruption on the screen. Sorry for that. So they are repelled upwards from the spikes and neutralize the negative charge on the clouds. They are repelled upwards by the spikes. And they're the ones used now to neutralize the negative charge on the clouds and neutralize the negative charges on the clouds. That is how the lightning arrestor functions. This is a very healthy paper. Very healthy paper. Thank you for following us. Please remember to subscribe. Remember to share this lesson with your friends. See you online. See you in our programs. Remember to enroll. My number is already indicated here, 070415 3366. Thank you so much.